This is my lab report for Lab 2, Motion of a Falling Object. The objective of this experiment was to observe the motion of an object that is dropped from rest and show that this motion follows Newton's second law by comparing the computational data obtained from our model to the experimental data analyzed in Tracker. Here's the equation for Newton's second law. It is important to note that in this experiment the object is not traveling with constant velocity. Therefore, F net is not equal to 0. So we must take into account the forces of gravity and drag when looking at the motion of this object. For this lab, I recorded a video of me dropping a fun-sized Milky Way. I then imported this video into Tracker to evaluate its motion. First, I ensured that the frame rate was correctly set to 30 frames per second. I set the calibration stick equal to my height, which is 5 feet 5 inches or 1.65 meters. The axis is set to that of a normal Cartesian plane, with the origin at the center of the Milky Way at t equals 0. And as you can see, the motion of the falling object is in the negative y direction. Next, I modified my code in order to generate a model of this experiment that only showed the effect of gravity. I changed the mass to equal that of the fun-sized Milky Way, which is 0.017 kilograms. Next, I changed the initial position vector to mimic that of the object's initial position found in Tracker. The object's initial velocity is equal to the vector 0, 0, 0 because it is falling from rest. For delta t, I chose a very small number to ensure enough data points would be predicted during the small duration of this experimental observation. G is the acceleration due to gravity, which is 9.8 meters per second squared. J hat represents the unit vector in the positive y-axis. The proportionality constant b here equals 0 because we are not taking into account the force of drag. Then I set the model to loop while t is less than 0.567 seconds, which is the final time used in Tracker. I used manipulations of Newton's second law in order to calculate the new velocity and new position vectors. I then set t equal to t plus delta t. Then I specified that gravity, noted here as W, was the only force to act on the object. Gravity is equal to the mass of the object times the acceleration due to gravity times the negative j hat. Here is what it looks like when I run my model. This is my position versus time graph comparing my experimental data to that of my computational model data. The two are similar, but as you can see, there are slight discrepancies. To try to get rid of these discrepancies between my model and experimental data sets, I added drag force to my computational model. I used the same model from before, editing a few lines of code. First, I stated that F net would now equal the force of gravity plus drag force. Drag force is equal to the magnitude of the object velocity times negative b, the proportionality constant. I found the value for b simply by guess and check methods. I knew that I had found the correct value for b when the final position of the object in the model nearly matched the final position of the Milky Way in Tracker. Next, I updated the arrows which show the forces acting on the object. I changed arrow 1 dot position and arrow 2 dot position to equal object position. I set arrow 1 to correspond to the force of gravity on the object and arrow 2 to correspond to the drag force. I also had to change the color of arrow 2 to red to make it easier to see because it was so small. Here's what my model, where F net is equal to the force of gravity plus drag force, looks like when I run it. Here is a position versus time graph of my observed data shown in the green points and my model with drag and without drag shown with blue and red lines respectively. As you can see, the computational model with drag and my experimental model form almost the same line, showing that my experiment was successful. Terminal velocity is the velocity of the object when the sum of the upward force of drag and the downward force of gravity are equal to 0. So when we plug this into our equation for Newton's second law, F net equals 0, meaning that V final must equal V initial. This is not the case for either of these models because F net is not equal to 0, so the velocities of the object is continuously changing as it falls. Therefore, neither of these models predict terminal velocity. If the object was initially thrown downward, the terminal velocity would be different from the case where it was dropped from rest. This is because, as I stated before, terminal velocity is the point in the fall of an object where F net becomes 0, meaning V final equals V initial. So an object thrown would have a greater initial velocity, and then a greater terminal velocity than an object that is dropped from rest. The two will, however, travel in the same direction.